Well, today we'll start our discussion on the next topic in this course that is based on advanced structural design of civil engineering structures that are implemented in practice, including a wide range of structures that may be building structures or bridge structures or other civil engineering structures that have to be designed according to the principles and practices of structural design. As we mentioned in the beginning of the course, the various civil engineering structures that will be considered in this particular course will be constructed of one of the two most popular materials for construction of civil engineering structures, that is concrete, specifically reinforced concrete, and steel. Steel and reinforced concrete are the two most popular or common construction materials for fabricating or constructing civil engineering structures in practice due to their relatively superior mechanical properties such as strength, stiffness, ductility, and also durability. Recall that the various civil engineering structures that are included in the scope of the present course CVL 441 can be broadly classified into two distinct categories based on the primary construction material that is used for constructing or fabricating the structure on the field or the site. And the present topic on which we will be beginning our discussion today is based on the structural design of an important and common civil engineering structure, that is the steel gantry or steel girder. And the next few lectures will be devoted to discussion of background theory for the structural analysis and design of steel crane or steel gantry girders, as well as illustrating the structural design process for steel gantry girders by means of a solved example that will include guidelines for solution of assignment number 3 as well. So we'll commence our discussion on the second component of the course CVL 441, that is the component that concerns the structural design of steel structures for civil engineering applications with concentration or focus on the structural design process for steel gantry or steel crane girders. Recall that the first component of the course outline or course content that was mentioned in the course outline and syllabus published on the Moodle website was based on structural design of reinforced concrete structures. That's the most popular material for construction of civil engineering structures. With this lecture, we will start our discussion on the structural design of steel structures, since steel is an equally popular or common material that is implemented for the fabrication or construction of civil engineering structures. And the first topic in our discussion on structural design of steel structures would be the design process for steel gantry or steel crane girders. So, beginning our discussion on the structural design process for steel gantry girders or steel crane girders, that is the first topic in the second component of this course based on design of steel structures. Introducing the function of a gantry girder or definition of a gantry girder. The function of a gantry girder is to support the rails on which the overhead traveling cranes move, generally in an industrial structure where overhead traveling cranes are almost invariably provided. For example, aircraft hangars, warehouses, factories, and and manufacturing plants, as well as hydroelectric and thermal power plants, in which heavy machinery, materials, and objects have to be moved routinely, and for this purpose the overhead cranes are required to lift and move such heavy machinery, materials, or objects in general from one part of the building to another. Well, proceeding to the structural design of a steel gantry girder or steel crane girders, the structural design process of a steel gantry or crane girder is a specialized task, as gantry girders are subjected to special loads that are characteristic or typical to the function of the crane or gantry girders. And the typical loads that generally act on a gantry girder or a crane girder and have to be considered in the structural design of the steel or gantry girder based on the characteristic function of the gantry girder are: 1. Vertical loads due to the weight of the crane and its payload, that is the payload of the crane, which is the weight of the object or the machinery or the equipment that has to be lifted and moved by the crane from one part of the building to another. 2. The horizontal dynamic force in the transverse or the horizontal x direction termed as the horizontal transverse dynamic load due to the acceleration on braking of the loaded trolley, known in common jargon as the crab of the crane, as well as the swinging of the suspended load in the horizontal transverse direction. The specific line of action of the horizontal transverse load due to acceleration and braking of the loaded trolley or crab of the crane and swinging of the suspended payload are shown in the figure that displays the schematic or the general arrangement of a industrial structure that is installed with a overhead electric crane and is supported by a steel crane or gantry girder. Referring to the schematic figure illustrating the general arrangement drawing of an industrial building that is provided with a gantry or a crane supported by a typical crane or gantry girder that happens to be provided with a fin type roof truss as shown here. The third specialized load that the steel gantry girder or the crane girder is subjected to, and that has to be accounted in the structural design of the steel gantry girder or the steel crane girder supporting the crane or the gantry, is the horizontal dynamic force in the longitudinal or the y direction, termed as the horizontal dynamic longitudinal load, that is induced by the acceleration and braking of the entire crane as a whole. In common jargon, the second component of the horizontal dynamic load acting in the y direction or the longitudinal direction along the y-axis as shown in the coordinate axis in the figure is, in addition to the horizontal dynamic force acting in the x direction that we mentioned in the previous slide, which is the horizontal dynamic transverse load acting in the transverse x direction with reference to the coordinate axis shown in this figure or schematic. Well, to highlight or distinguish the fundamental difference between the second and the third type of specialized load, that is the horizontal dynamic transverse load, due to the acceleration and braking of the suspended payload as well as the acceleration and braking of the loaded crab or the crane trolley, which is accompanied by swinging of the suspended payload in the horizontal transverse direction x, and the horizontal dynamic force termed as the horizontal dynamic longitudinal load acting in the longitudinal y direction. The characteristic of the horizontal dynamic longitudinal load acting in the longitudinal y direction is conceptually different from the horizontal dynamic transverse load acting in the x direction that was discussed in the previous slide. Since the horizontal dynamic longitudinal load is induced by the acceleration and braking of the entire crane as depicted by this truss right here, that is the structural system of the entire crane. Effectively caused by the surge or impact of the crane, while the horizontal dynamic transverse load that was discussed in the previous slide as one of the special or specialized loads acting on gantry or crane girders acts by the virtue of the acceleration and deacceleration of the loaded crab or trolley of the crane, that is depicted by this rectangle on circles, where the rectangle represents the crab or the trolley of the crane that moves in the transverse direction, that is the horizontal transverse direction x, as well as the swinging of the payload of the crane that is depicted by this weight with the symbol W in the horizontal or transverse direction x. Therefore, one may intuitively visualize that any suspended payload, for example, payload W of the crane depicted in this schematic figure of an industrial building, should have 3 degrees of freedom by the virtue of the permissible motions of the crane, the loaded trolley or the crab of the crane, and the vertical lifting or lowering of the payload by means of a pulley mechanism such as the one shown in this schematic figure. And these 3 degrees of freedom that the suspended payload is provided with are the vertical movement due to lifting or lowering of the payload by means of a typical pulley mechanism. And the horizontal transverse motion due to the movement of the loaded trolley or crab in the horizontal transverse direction X over the crane, as well as the horizontal longitudinal motion along the longitudinal x-axis as shown by the frame of reference for this schematic figure. The longitudinal y-axis along the longitudinal y direction of the building. Illustrated as a typical industrial building in this schematic or figure. Thus, the crane or the gantry enables or imparts the movement or motion of the payload represented by the symbol W in the schematic or figure in all the three directions, that is, all along all the three coordinate axes. That means the degrees of freedom along all the three directions the X or the horizontal transverse direction due to the movement of the loaded trolley that can translate in the horizontal transverse direction on the crane. The movement in the horizontal longitudinal direction, that is the y direction, along the coordinate axis y, due to the movement or motion of the entire crane with the loaded trolley along the horizontal longitudinal direction y, and the movement or motion of the suspended payload denoted as capital W in the upward or downward vertical direction, that is the Z direction. enabled by the lifting or lowering of the suspended payload W along the coordinate axis Z by the pulley mechanism that is depicted in this schematic or figure. Continuing our discussion on the typical design loads that need to be considered in the structural design of gantry girders or crane girders, defined as the girders or beams, in a sense, that support the rails on which the overhead traveling cranes move. The gantry girder or the crane girder, which in this case, in the present context, is a steel gantry or steel crane girder as depicted by this I section in the schematic figure displayed in this slide. The fourth typical design load is the self-weight of the crane girder or the gantry girder. That is the dead load due to the self-weight or the dead weight of the steel gantry girder or the crane girder, which in a larger perspective is actually a typical design load that is considered in the structural design of any civil engineering structure, as the dead weight or the self weight of the structure has to be accounted in the structural design of the respective civil engineering structure. And as in case of any civil engineering structure, the self weight of the crane girder or the gantry girder depicted in this schematic figure is considered as a static load or a dead load that is caused by the self weight of the steel gantry girder. Elaborating on the other details that are included in this general arrangement drawing of an industrial building provided with a gantry or a crane that is supported on a steel gantry girder or a steel crane girder, as depicted in this isometric view of the industrial building with the steel gantry girder or crane girder highlighted in black ink. The general terminology for an industrial building structure based on the typical structural components of an industrial building structure are labeled in this schematic figure of the industrial building structure. Generally, the industrial building structure consists of a roof truss, which is commonly a fink type truss that is supported on columns and along the length of the building, that is in the longitudinal y direction of the building, there may be at least two or more such roof trusses. For example, the fink type roof truss shown in this schematic figure, and replications of similar roof truss, for example truss 2 and truss 3 and so on and so forth, depending on the length of the industrial building structure along the longitudinal y axis. Within this structural system for the industrial building structure that is illustrated by the general arrangement drawing of the industrial building as depicted in this schematic figure, the steel crane or steel gantry girder that supports the rails on which the overhead traveling crane moves is supported on brackets that are also constructed or fabricated in steel and are connected to the columns as depicted in the schematic figure of the industrial building structure. The aisle width, that is the width of the aisle of the industrial building, generally the dimension of the industrial building in the horizontal transverse direction x is the span of the crane that is provided in the industrial building with some minor deductions due to the location of the supports for the crane or the gantry. However, more or less the aisle width A of the industrial building, that is the width or the dimension of the industrial building along the horizontal transverse direction x as depicted in this schematic figure, is more or less equal to the span of the crane that is to be provided or installed in the industrial building based on the manufacturer specifications for the dimensions of the crane. Note that the span of the crane, that is more or less equal to the aisle width of the industrial building, is different from the span of the crane girder or the gantry girder that supports the rails on which the overhead electric crane moves. The span of the crane girder or the steel gantry girder in this context, denoted as capital L, is the unsupported length of the steel gantry girder or the steel crane girder, as highlighted by the black ink in this schematic figure, between two adjacent supports. In this case, since the steel gantry or the steel crane girder is supported on brackets that are connected or fastened to the columns of the industrial building, the span L of the crane girder or the steel gantry girder is the distance between the two adjacent columns that are supporting the brackets on which the steel crane girder or the gantry girder is installed. It is worthwhile to mention that the center to center spacing or the distance between the columns that support the brackets on which the steel gantry girder or steel crane girder is installed in an industrial building provided with a overhead electric crane, or in general in any industrial building structure, is also termed as the bay length. That is the length of a bay in the industrial building. And in general, an industrial building can have several bays ranging from at least one bay to the number of bays that may be required depending on the length of the industrial building along the longitudinal y direction. Therefore, based on our discussion on the typical design forces that need to be considered in the structural design of gantry or crane girders, the design loading for steel gantry girders or steel crane girders can be simplified to consist of three components. One, concentrated vertical force V that acts on the top flange of the steel gantry girder or crane girder, illustrated in this figure as a built-up beam due to the weight of the crane and the loaded trolley or the crab of the crane. Two, the concentrated dynamic horizontal transverse force T acting in the transverse X direction. With reference to the coordinate axis displayed in the schematic figure of a typical industrial building that is provided with a overhead electric crane or a gantry supported on rails at either end that are installed on the top flange of the steel or gantry girder, that is steel crane girder, for which a typical cross section is shown as a built-up beam in this figure. Three, the horizontal dynamic longitudinal force L acting in the longitudinal Y direction of the building with reference to the schematic of a typical industrial building that is provided with the overhead electric crane traveling on rails installed on the top flange of a steel gantry girder or a steel crane girder, as displayed in isometric view in the previous slide. And three, rather fourth design load that needs to be considered for the structural design of steel gantry or steel crane girders, in addition to the three special loads that are characteristic of gantry or crane girders, is the uniformly distributed self-weight of the rail and the gantry or the crane girder itself. Obviously, the uniformly distributed self-weight of the rail and the gantry girder itself is the dead load. That is a static load that acts by the virtue of the self-weight or the dead weight of the rail and the girder, and is therefore a common design load that is considered for structural design of any structural element in general. It is worthwhile to mention here that the concentrated dynamic horizontal transverse force T that acts in the transverse x direction with reference to the coordinate axis displayed in the schematic for the typical industrial building structure that is provided with an overhead electric crane traveling on rails that are installed on the top flange of a steel gantry girder or a steel crane girder, illustrated in this figure as a built-up beam, is induced by the acceleration and braking of the loaded trolley or the loaded crab of the crane that moves in the horizontal transverse direction X of the industrial building, for which the schematic diagram is shown in the previous slide, while the horizontal dynamic longitudinal force L that is deemed to act on the top flange of the steel gantry girder or steel crane girder, illustrated as a built-up beam in this figure, is generated by the acceleration and braking of the crane as a whole. Therefore, with that review of the previous discussion based on the previous slide, one can visualize in physical terms that the design loading that needs to be considered for structural design of steel gantry or steel crane girders in a typical industrial building provided with a overhead electric crane that travels on the rails which are installed on the top flange of the steel gantry girder or the steel crane girder, illustrated as a built-up beam in this figure, is induced or are induced or exerted and transmitted from the overhead electric crane to the rails through the top flange of the steel gantry or steel crane girder that supports the rails on which the overhead traveling crane moves. And since each crane or gantry in common jargon is supported on two wheels at each of the ends of the crane, as illustrated in the schematic diagram for the industrial building in the previous slide. The rail on which the overhead traveling crane moves, as well as the steel crane or gantry girder that supports the rail, is subjected to two wheel loads as the crane moving on the rails is supported on two wheels at each end. Therefore, each rail installed on the steel gantry or steel crane girder at either end of the industrial building transmits two wheel loads that are idealized as moving loads from the wheels through the rails to the top flange of either and each steel gantry girder or steel crane girder that supports the rails at each end on which the overhead electric cranes move. Since the overhead electric crane travels on the rails, that is one rail at each end of the overhead electric crane, as shown in the schematic diagram of the typical industrial building structure that is provided with an overhead electric crane in the previous slide. And the overhead electric crane is supported by two wheels at each end. That is, two wheels on each rail. The design loads, including the special dynamic forces that are induced by the overhead electric crane, moving on two rails, one at each end, with each rail installed on a steel gantry girder or steel crane girder, illustrated in this figure as a built-up beam. Are distributed among the two wheels acting as moving wheel loads on each rail or steel gantry girder at either end of the overhead electric crane. Hence, the concentrated vertical force V due to the weight of the crane and the loaded trolley of the crane or the loaded crab of the crane, including the payload of the crane, and the concentrated dynamic horizontal transverse force T acting in the transverse X direction of the industrial building structure, for which the schematic diagram is shown in the previous slide, that is induced by the acceleration and braking of the loaded trolley or the loaded crab of the overhead electric crane, as well as the swinging of the payload in the transverse X direction. of the industrial building with reference to the schematic diagram of the industrial building structure that is shown in the schematic figure in the previous slide. And the horizontal dynamic longitudinal force L that is induced in the longitudinal y direction of the industrial building for which the schematic diagram is illustrated in the previous slide, are distributed or shared by each wheel on which the overhead traveling crane moves, and therefore one has to calculate the design loading that is induced by the overhead electric crane traveling on wheels that move on the rails installed on the top flange of each steel gantry girder or steel crane girder. For which the figure in this slide depicts the built-up beam section. While the concentrated dynamic horizontal transverse force induced in the x direction of the industrial building displayed in the schematic presented in the previous slide, and the horizontal dynamic longitudinal force L induced by the overhead electric crane in the longitudinal y direction of the industrial building and transmitted through the rails by means of wheels that move on the rails with two wheels at each end of the overhead electric crane that are moving on the rail installed on the top flange of the steel gantry girder or steel crane girder, displayed as a built-up beam in this figure. The moving wheel loads corresponding to each of the two wheels at either end of the overhead electric crane that are transmitted to either rail and either steel gantry or steel crane girder on which the rail is installed at each end of the overhead electric crane are assumed to be equal. That is, the concentrated dynamic horizontal transverse force T induced by the overhead electric crane in the transverse X direction and the horizontal dynamic longitudinal force L induced by the overhead electric crane in the longitudinal Y direction of the industrial building, displayed in the schematic diagram in the previous slide, are assumed to be equally distributed among or equally shared by each wheel at either end of the overhead electric crane that moves on the rails installed on the top flange of the steel gantry girder or steel crane girder, illustrated as a built-up beam in this figure. And therefore, each steel gantry girder or steel crane girder shown as a typical built-up beam section in this figure shares or resists an equal share of the concentrated dynamic horizontal longitudinal force and the concentrated dynamic horizontal transverse force that are transferred through the rails to the top flange of each steel crane or steel gantry girder. On the other hand, the concentrated vertical force V due to the weight of the crane and the weight of the loaded trolley or the crab of the crane will be distributed among the two rails at each end of the overhead electric crane depending on the location or the position of the loaded trolley or the loaded crab along with the suspended payload. To summarize the discussion on the design loading that is considered to act on steel gantry or steel crane girders for purposes of structural design, the design loading, including the special dynamic loads, special dynamic forces, characteristic of overhead electric cranes, are generally distributed through two wheels at each end of the overhead electric crane that move on a rail at each end of the overhead electric crane. And since the rails are installed on steel gantry girders or steel crane girders, illustrated as a built-up beam section in this figure, the special dynamic loads, that is the concentrated horizontal dynamic transverse force T and the concentrated horizontal dynamic longitudinal force L, are idealized to be transmitted from the overhead electric crane through the rails on which the two wheels at each end of the overhead electric crane moves to the top flange of the steel gantry girder or steel crane girder. Assuming that the special dynamic forces or special dynamic loads for example, the idealized concentrated dynamic horizontal force T and the idealized concentrated horizontal longitudinal force L are equally distributed to the four wheels with two wheels at each end of the overhead electric crane and further transmitted through the rails to the top flange of the steel gantry girder or steel crane girder. And therefore, the special dynamic forces or special dynamic loads that are characteristic of the steel crane girders or steel gantry girders, that is the dynamic horizontal transverse force T and the dynamic longitudinal force L, are assumed to be equally distributed or equally shared by the two steel gantry girders or steel crane girders at each end of the overhead electric crane. With that background, we can proceed to calculate the design loading for a steel gantry or steel crane girder for the purposes of structural design, including the special dynamic loads or the special dynamic forces that are characteristic of steel gantry or steel crane girders. Well, the design loads are in general governed by the size and capacity, also termed as payload, of the overhead electric crane. Since overhead electric cranes vary considerably in sizes and capacities based on the wide variety of commercial overhead electric cranes that are available in the market, ranging from light hand-operated models to heavy power-operated cranes or gantries. For example, the heavy power-operated cranes that are generally provided in hydroelectric power plants or thermal power plants. The design data pertaining to the sizes, dimensions, weights, and clearances of the overhead electric cranes that are commercially available show significant variation due to the large variety of the overhead electric cranes that are manufactured in the industry and are generally provided by the manufacturer's specifications for the particular crane or gantry model that is to be installed in the industrial building of interest, for which the steel crane gantry girder or the steel crane girder is to be designed. In other words, due to the large variation in the sizes, dimensions, weights, and clearances that are provided by the manufacturer specification for different commercially available models for cranes or gantries, that is, the commercial products for overhead electric cranes or overhead electric gantries. For purposes of structural design of the steel gantry or the steel crane girder, for example, the steel gantry or the steel crane girder illustrated as a built-up beam section in this figure is generally based on typical design data. For generic models of overhead electric cranes, in the absence of the manufacturer's specifications for the specific model of the overhead electric crane that is to be installed. However, it is recommended that if the manufacturer's specifications for the specific model of the overhead electric crane or the overhead electric gantry is available, then the design data should be based on the manufacturer's specifications. The typical design data for some generic models of overhead electric cranes is displayed in the table shown in the annexure at the end of the presentation and will be referred to for the structural design of steel crane or steel gantry girders. In the assignment number 3, as well as the solved example that we will be discussing in the future, for illustrating the guidelines to the solution to the assignment number 3, and the typical design data that is provided in the table included in the annexure of this presentation as well as uploaded on the assignment question published on the Moodle website for the course. Presents the typical sizes, dimensions, weights, and clearances for some common, popular, and generic models of overhead electric cranes, and thus are sufficiently useful for the purpose of discussion in this course, as well as sufficiently purposeful for the solution to the question in assignment number 3, as well as the solved example that will be discussed in the next few slides to illustrate the guidelines for the solution of the question in assignment number 3. Continuing our discussion on the background theory for structural analysis of steel gantry or steel crane girders based on the mechanics and the path of load transfer from the overhead electric crane or gantry to the individual steel gantry or crane girders. Recall that the typical design data for standard overhead electric cranes that are generally provided in industrial building structures such as aircraft hangars, rolling mills, steel plants, and hydroelectric power plants or thermal power plants. Is provided by most texts and design manuals in the form of a table or a tabular format for the various tolerances, clearances, dimensions, capacities of the overhead electric cranes that are commercially available in the market. An example of the typical design data for structural design process of steel gantry or steel crane girders for standard overhead electric cranes that are commercially available in the market is provided in tabular format in the annexure presented at the end of this PowerPoint discussion, as well as the Moodle website of the course in PDF format, along with assignment number 3 that is based on the structural design process for steel gantry girders or steel crane girders. For the purposes of discussion of the structural design process for steel gantry girders or steel crane girders, we will be referring to the standard data on overhead electric cranes as presented in the table that is provided along with the assignment number 3. That is based on the structural analysis and design of steel gantry girders or steel crane girders. Additionally, the typical design data for overhead electric cranes that is required for structural analysis and design of steel gantry or steel crane girders, as in case of the solved example that will be discussed in the next few slides, for illustrating the detailed guidelines for structural analysis and structural design of steel gantry girders or steel crane girders will be referred to the table that is provided at the end of this PowerPoint presentation, on the structural design process for steel gantry girders or steel crane girders, and is included in the second page of assignment number 3 based on the structural design process for steel gantry or steel crane girders, that is published or assigned on the Moodle website for the course. Therefore, referring to the typical design data of the standard overhead electric cranes that are commercially implemented in practice, and required for the structural design process of steel gantry or steel crane girders. The structural design process may be explained in terms of a few tasks or steps, and the tasks or steps in the structural design process for steel gantry or steel crane girders are: 1. Select the appropriate overhead electric crane for the required application, since overhead traveling cranes range from light hand-operated cranes to heavy power-operated electric cranes. Depending on the application or the function of the overhead traveling crane that is required, for example, an overhead traveling crane in a institutional building, laboratory, that may be a light hand-operated crane ranging to a heavy power-operated overhead electric crane that would be required in a hydroelectric power plant. The particular or specific model or the specifications, for example, the manufacturer specifications of the required overhead traveling crane may be selected to serve the intended function. Step 1 is therefore part of functional design of the steel gantry or steel crane girder as the engineer in step 1 of the structural design process or the overall design process for steel gantry or steel crane girder selects the appropriate overhead traveling crane that can range from light hand operated cranes to heavy power operated overhead electric cranes depending on the application that may range from institutional laboratory to an industrial shed to a hydroelectric or thermal power plant in which very heavy duty power operated overhead electric cranes are deployed. Once the appropriate model and the specifications of the overhead traveling crane required for the specific application are selected by the design engineer in step 1 as part of the functional design in the design process for steel gantry girder or steel crane girder. The next step, that is step number 2, involves the calculation of the design forces or the design loads for the selected model and specifications of the overhead traveling crane in the functional design stage, that is step 1. And as discussed in the previous slide, the calculation of the design forces or design loads that are based on the background theory for structural analysis of steel gantry or steel crane girders as part of the structural design process, and require the application of the first principles of mechanics for idealizing the path of load transfer from the overhead traveling crane to the rails on which the overhead traveling cranes move, through the top flange of the steel gantry girder or steel crane girder on which the rails are installed. Considering the capacities, that is load capacities or payloads, dimensions, clearances and tolerances that are provided in the manufacturer's specifications for the specific model of the overhead traveling crane selected for the intended function. In the absence of the manufacturer's specification for the selected model of the overhead traveling crane that is selected for the intended function, in step 1, one may use or refer to the typical design data that is presented in the table titled as Typical Design Data for Overhead Electric Cranes, presenting the design parameters for that are required for the structural design of steel gantry or steel crane girders. Along with assignment number 3, on the second page of assignment number 3, that is published or assigned on the Moodle website for the course. It is worthwhile to note here that in case the manufacturer specifications on the dimensions, load capacities or payloads clearances and tolerances for the specific model of the overhead traveling crane that is selected for the required application are available, then in practice one should refer to the manufacturer specifications. However, due to the wide or large variation in the specifications of overhead traveling cranes that are available commercially, most textbooks and design manuals provide the typical design data corresponding to standard overhead electric cranes that is required for purposes of structural design of steel gantry or steel crane girders in a tabular format, and for purposes of discussion in this course as well as the solved example that is included in the lecture notes in the next few slides for illustrating the detailed guidelines for solution of assignment number 3. We will be referring to the typical design data provided by textbooks and design manuals, a sample or example of which is presented in the table on the second page of assignment number 3. With that background on the functional design stage of the structural design for steel gantry or steel crane girders, as addressed by step 1 of the design process for steel gantry or steel crane girders, and the previous discussion on the background theory based on the mechanics and path of the load transfer from the overhead electric crane to the steel gantry or steel crane girder for the calculation of the design forces or design loads. With reference to the manufacturer specifications or the typical design data for overhead traveling cranes provided in the table on page 2 of assignment number 3, we will proceed to the next step in the design process for steel gantry girders or steel crane girders, that is the structural modeling of the steel gantry girder for purposes of structural analysis and design of the steel gantry or steel crane girder under the action of the idealized design forces or design loads imposed by the overhead electric cranes. At this juncture, it would be sufficient to mention that in general, the steel crane girder or steel gantry girder is idealized or modeled for the purposes of structural analysis and design as a simply supported or a continuous beam spanning from column to column with the design forces considered to be acting at the level of the top flange of each steel gantry girder or steel crane girder that is provided at each end of the overhead electric crane to support the rails on which the overhead electric cranes move. The fourth step in the design process for the steel gantry or steel crane girders is the structural analysis of the mathematical model or the structural model that is idealized for representing the steel gantry girder or the steel crane girder for the purposes of the structural design of the steel gantry or the steel crane girder subjected to the design forces or the design loads that are calculated in step 2. Finally, the fifth step in the step-by-step design process that is discussed in the present slide for the structural design of steel gantry girder or steel crane girder is the structural design of the gantry girder, that is the rolled steel section or built up beam section or plate girder section that is selected for the steel gantry or the steel crane girder of interest, as well as the structural design of the brackets that support the steel gantry girder or steel crane girder and the columns that support the steel brackets, as well as the base plates of the columns on which the columns are resting. One may note that The rails, although being a part or a component that transfers the design forces or the design loads from the overhead electric crane to the steel gantry or the steel crane girder, and subsequently to the brackets, columns, and the steel base plates, up to the foundation of the columns in the industrial building. The rails are the rails on which the overhead traveling cranes move are mechanical products or are prefabricated products that are designed and manufactured in steel plants as prefabricated or pre-engineered steel products, and the design and manufacturing of the rails are not in the scope of the civil engineer, as the design and manufacturing of the rails on which the overhead traveling cranes move are in the scope of mechanical engineers. Therefore, structural engineer is concerned only with the structural design of the steel gantry girder or the steel crane girder and the steel brackets supporting the steel gantry or crane girder, as well as the columns and the steel base plates that transfer the design forces or design loads from the overhead electric cranes in the same sequence of load transfer in the path of load transmission to the foundation of the industrial building in which the overhead traveling crane is implemented or provided. Therefore, proceeding to the third step in the structural design process for steel gantry girders or steel crane girders, that is based on the mathematical modeling or structural modeling of the steel gantry or the steel crane girder for the purposes of structural analysis of the gantry or the crane girder under the action of the design loads, including the special design loads that are dynamic forces in nature due to the specific function or the specific application of the steel gantry girder or steel crane girder, that is to support the rails on which the overhead traveling cranes move. The gantry girder is modeled, analyzed and designed as a simply supported or continuous beam spanning between the adjacent columns with no intermediate lateral support to the girder as assumed usually, unless a walkway is provided at the level of the top flange of the steel gantry girder or steel crane girder for the purposes of inspection or maintenance of the overhead electric crane that is supported by the gantry girder. As in case of some heavy power operated cranes that are installed in large industrial building structures such as hydroelectric power plants or thermal power plants. In this case, where a walkway is provided at the level of the top flange of the steel gantry or the steel crane girder for the purposes of inspection or maintenance of the overhead electric crane, the top flange of the steel gantry girder or the steel crane girder is assumed to be laterally supported or restrained. Since the walkway is deemed to provide adequate lateral support or restraint to the top flange of the steel gantry girder or the steel crane girder. However, bearing this special case, that is, with the exception of this special case wherein a walkway is provided at the level of the top flange of the steel gantry or the steel crane girder that provides effective lateral support or lateral restraint to the top flange of the steel gantry or steel crane girder. In general, the gantry girder or the crane girder is idealized or modeled as a laterally unsupported beam, that is, beam with unrestrained compression flanges, that is spanning from column to column with simple or continuous supports, and therefore the unsupported length or the span length L of the idealized mathematical model for the gantry girder has a span length L that is equal to the unsupported length or the distance between the adjacent columns on which the brackets or the supports of the steel gantry girder or steel crane girder are installed. In other words, for the purposes of structural analysis of the steel gantry or the steel crane girder, under the action of the design loads, including the special design forces that are characteristic of the function of the steel gantry or the steel crane girder. For example, the concentrated dynamic horizontal force L in the longitudinal or the y direction of the industrial building, and the concentrated horizontal dynamic transverse force T in the transverse x direction of the building, as well as the concentrated vertical force due to the weight of the crane and its payload acting in the negative Z direction of the industrial building structure, as illustrated in the schematic diagram for the industrial building structure that is provided with an overhead electric crane in one of the previous slides, along with the choice of the coordinate axis X, Y, and Z for depicting the directions of the design forces or the design loads acting on the steel gantry or the steel crane girder. The structural modeling or the mathematical modeling of the steel crane or the steel gantry girder is based on the idealization of the gantry girder as a laterally unsupported beam, that is, a beam with unrestrained compression flanges with the span length or unsupported length between the adjacent supports or brackets or the columns. For the purposes of the structural analysis of the steel gantry girder or the steel crane girder subjected to the design loads that have been discussed in quite some detail in the previous slide. It is worthwhile to note here that the self weight of the steel gantry girder itself, as well as the rail that is installed on the steel gantry girder that supports the overhead electric crane, need to be considered in the structural analysis of the steel gantry girder or the steel plate girder. Further, it is noteworthy that the steel gantry girder or crane girder is more commonly modeled as laterally unsupported beam with simple supports rather than continuous supports. That is, the structural modeling of the steel gantry or the steel crane girder is based on the idealization of simply supported spans instead of continuous spans for the purposes of structural design. In design practice, as the maximum bending moment that occurs in a continuous beam of span length L as depicted in this figure, that is the unsupported length between the adjacent support denoted as capital L in this figure, is always less than the maximum moment M max, that is denoted as capital M subscript max and is equal to QL square by 8 in a corresponding simply supported beam with identical span length capital L. And since the maximum bending moment that can be induced in a continuous beam as depicted in this figure is limited to the maximum value of the bending moment, denoted as capital M subscript max, for a corresponding simply supported beam with identical unsupported length between the supports, that is span length denoted as capital L between the supports, which is equal to the unsupported length or the span length of the continuous beam in practice. The gantry girder is modeled as a simply supported beam. Since the assumption of simple supports results in the most conservative value of the maximum bending moment. In other words, in practice, for the purposes of structural analysis of steel gantry or steel crane girders, the steel gantry girder is generally modeled as a simply supported beam with laterally unsupported compression or top flanges, although in reality the practical steel gantry girder or steel crane girder is in fact a continuous beam spanning over continuous supports since the maximum absolute values of the bending moments that occur in a continuous beam subjected to a uniformly distributed load of intensity Q in kilonewton per meter, for example, as well as the maximum absolute value of the bending moments at the continuous supports denoted as MS, that is capital M subscript S, where the subscript S denotes the bending moment at the support, is always less than or limited by the maximum bending moment M max that occurs or is induced at a corresponding simply supported beam subjected to an identical uniformly distributed load, or UDL, of intensity equal to Q in kilonewton per meter, and has the identical unsupported length between the simple supports, that is equal to the span length of the corresponding simply supported beam. Continuing our discussion on the structural design process for steel crane or steel gantry girders, the fourth step in the step-by-step methodology presented in one of the earliest slides for the structural design of steel gantry girders or steel crane girders is the structural analysis of the steel gantry girder, steel crane girder, under the action of the common or routine, that is normal design loads such as the self weight of the gantry girder and the rail installed on the top flange of the gantry girder, as well as the concentrated vertical force acting on the top flange of the steel crane or steel gantry girder, that is in the negative Z direction with reference to the coordinate axis illustrated in this figure, and the special dynamic loads that are characteristic of the function of the steel gantry girder or the steel crane girder, that is to support the rails on which the overhead traveling cranes move, and these special dynamic design loads that are generated by the virtue of the motion or the dynamics of the overhead electric crane that moves on the rails installed on the top flange of the steel crane or steel gantry girder are the horizontal transverse force, which is a dynamic force acting in the transverse x direction, and the horizontal dynamic longitudinal force denoted as L, that is induced in the longitudinal y direction of the industrial building structure in which the overhead electric crane is installed, with reference to the schematic diagram of the industrial building structure, illustrating the isometric view of the industrial building structure, along with the choice of the coordinate axis, as shown in the schematic diagram presented in one of the earlier slides, and also reproduced in this figure as the Cartesian coordinates, or the coordinate axis x in the transverse direction of the industrial building, the longitudinal axis y in the longitudinal y direction of the industrial building, and the vertical z axis the positive direction of which can be obtained from the right hand thumb rule for Cartesian coordinate system, that is illustrated in this figure displaying the cross section of the steel crane gantry girder or steel gantry girder based on the practical considerations of the mechanics of steel crane gantry girders, or the mechanics of the load transfer path from the overhead electric crane to the steel crane or steel gantry girder supporting the overhead electric crane, the structural analysis of the steel crane or the steel gantry girder can be considerably simplified without any loss of accuracy or without significant loss of accuracy by making the following simplifying assumptions in the structural analysis of the steel gantry girders or the steel crane girders. And these simplifying assumptions that are typically employed for the structural analysis of steel gantry girders or steel crane girders are: one, that the horizontal transverse force denoted as capital T acting in the transverse x direction due to the acceleration and braking of the loaded trolley or the loaded crab of the overhead electric crane, as well as the swinging of the payload of the overhead electric crane, and the horizontal longitudinal force denoted as capital L, that is generated by the acceleration and braking of the crane as a whole, that is the entire crane, moving in the longitudinal y direction of the industrial building with reference to the coordinate axis defined in the schematic diagram for the industrial building structure. Presented in one of the earlier slides. Are assumed never to act together. In other words, the horizontal dynamic transverse force denoted as capital T and the horizontal longitudinal dynamic force denoted as capital L, both of which are dynamic forces or special design loads that act by the virtue of the surge and impact or the motion of the overhead electric crane and its components such as the trolley and the swinging payload do not act together. In other words, only one of the horizontal dynamic forces, that is either the horizontal transverse dynamic force T or the horizontal longitudinal force L, act at any given time. The physical reasoning for this simplifying assumption number one is that the horizontal dynamic transverse force T is induced by the acceleration and braking of the loaded trolley or crab of the overhead electric crane in the transverse x direction, as well as the swinging of the payload of the crane in the transverse x direction, while the longitudinal horizontal dynamic force L is generated by the acceleration and braking, that is induced by the surge or impact of the crane in the longitudinal y direction. Since the entire crane, along with the loaded trolley and the swinging and the suspended payload are capable of moving in the longitudinal y direction, and these two horizontal dynamic forces, that is the horizontal dynamic transverse force T and the horizontal dynamic longitudinal force L, generally do not act together, because the instructions of the standard instructions for operating the crane prohibit the movement of the crane in the longitudinal direction L, as well as the movement of the loaded trolley or the crab in the transverse direction. That is, the standard operating instructions for the crane do not allow simultaneous motion of the loaded trolley or the crab in the transverse x direction and the entire crane in the longitudinal y direction, and thus only one of the two horizontal dynamic forces, that is either the horizontal dynamic transverse force T or the horizontal dynamic longitudinal force L, should act at any given time. The second simplifying assumption for simplification in the structural analysis of the steel gantry girder, the steel crane girder, is to decompose the horizontal dynamic forces and the vertical design forces so as to simplify the structural response of the steel crane gantry girder into similar, that is, elementary components such as uniaxial bending and torsion. Well, strictly the gantry girder should be analyzed as a beam subjected to biaxial bending about both the major axis XX as well as the minor axis YY of the girder or the beam, and torsion about the longitudinal axis YY of the beam. In other words, while a rigorous structural analysis of the steel gantry or the steel crane girder would require the consideration of biaxial bending combined with torsion, since the gantry girder in reality undergoes bending about the major axis XX of the cross section of the girder due to the horizontal dynamic longitudinal force L acting at the level of the top flange in the longitudinal y direction, as well as the vertical force V acting also at the level of the top flange of the girder due to the weight of the crane and its payload, including the self-weight of the gantry girder itself and the rail installed on the gantry girder. And also undergoes bending about the minor axis ZZ of the girder as depicted in this figure. Due to the transverse longitudinal dynamic force T acting in the transverse x direction with reference to the coordinate axis, illustrated in this figure as well as the schematic diagram for the industrial building structure in which the overhead electric crane is installed in one of the earlier slides. And the bending about the major axis X of the girder cross section, that is illustrated in this figure, and the bending about the minor axis Z of the girder cross section is accompanied by a torsional rotation of the girder cross section as qualitatively illustrated in this figure due to the eccentricity of the transverse horizontal dynamic force T with respect to the centroid of the girder cross section. Therefore, rigorously, the gantry girder cross section or the steel crane girder cross section is subjected to biaxial bending, that is bending about the major axis X as well as bending about the minor axis Z, combined with torsion. And since the cross section of the steel gantry girder or steel crane girder is non-circular, the cross section undergoes warping or the torsion of the non-circular cross-section results in warping of the cross-section, a complex physical phenomenon that is observed in structural beam elements subjected to torsion that do not have a circular cross-section. Recall from your basic first year undergraduate course on solid mechanics that torsion in an element with a circular cross-section, that is a cylindrical element, results in Saint Venant's or pure torsion, while torsion in an element that is non-cylindrical or has a non-circular cross-section results in warping of the cross-section, which needs to be modeled separately. And since the theoretical modeling of the structural behavior of the steel crane gantry girder that is subjected to biaxial bending about both the major XX axis and the minor ZZ axis, combined with torsion about the longitudinal Y axis, is a somewhat complex task and rigorous theoretical modeling of the structural behavior of the gantry girder or the crane girder, considering biaxial bending combined with torsion, presents a complex and cumbersome task. For simplicity in structural analysis, for the purposes of structural design, in practice, it is assumed that the transverse horizontal dynamic force T can be decomposed into two components. The first of which is an antisymmetrical component as shown in the left figure on the slide, with antisymmetrical forces of magnitude T by 2 acting at the level of the top flange and bottom flange respectively, superimposed with the second component that are symmetrical components, both of which of magnitude equal to T by 2, acting on the top flange as well as the bottom flange of the gantry girder cross section. It is intuitive that this simplifying assumption should not result in any significant loss of accuracy, since the total horizontal dynamic transverse force T acting at the level of the top flange of the steel crane gantry cross section has been simply decomposed into two components, first of which consists of antisymmetrical forces of half the magnitude of the horizontal dynamic transverse force T acting on the top flange and bottom flange respectively, while the second component consists of symmetrical forces of half the magnitude of the horizontal dynamic force acting in the transverse x direction. Acting on the top flange as well as the bottom flange of the crane girder cross section, and superimposing the two components, this antisymmetric component with the symmetrical component of the horizontal dynamic transverse force T, one can easily verify that the forces acting, the force components of the horizontal transverse force T acting on the bottom flange cancel each other out or balance each other, and therefore may be cancelled against each other, thus leaving only the force components acting on the top flange, each of which are equal to half the magnitude of the horizontal dynamic transverse force T acting in the transverse x direction on the top flange of the steel plate girder or steel gantry girder. Well, while the second simplifying assumption, that is the simplification or decomposition of the horizontal dynamic transverse force T into symmetrical and anti-symmetric component, does not offer any advantage in the computational effort or calculations of the stresses in the crane girder or gantry girder cross section. The simplification or decomposition of the horizontal dynamic transverse force T into the anti-symmetrical case and the symmetrical case lends itself to a very convenient and useful insight or visualization into the real physical behavior or structural response of the gantry girder under the action of the various design forces. It is intuitive that the anti-symmetrical components of the horizontal transverse dynamic force T obtained from the decomposition of the transverse force T into antisymmetrical and symmetrical components results in torsion of the non-circular girder cross section. While the symmetrical components of the horizontal dynamic transverse force T obtained from the decomposition of the transverse force into an antisymmetrical arrangement and a symmetrical arrangement results in uniaxial bending of the girder cross section about the minor axis Z of the cross section, thus providing insight into the real physical behavior for the purposes of the mathematical modeling of the theoretical structural response of the gantry girder under the action of the multi-directional design loads or design forces. The decomposition or simplification of the horizontal dynamic transverse force T in the transverse x direction of the gantry girder as depicted in any of these figures due to the acceleration and braking of the loaded trolley or the loaded crab of the overhead electric crane, as well as the swinging of the payload of the crane in the transverse x direction. Therefore, provides the physical reasoning or the physical explanation of the real structural response or physical behavior of the gantry girder, that is, biaxial bending combined with torsion and the torsion is experienced due to the antisymmetrical components of the horizontal dynamic transverse force T, resulting in warping stresses due to the non-circular cross-section of the crane girder or the gantry girder. Based on the idealization of the structural response or the real physical behavior of the steel crane girder or steel gantry girder, the cross section of which is shown in this figure, as presented in the previous slide, under the action of the design loads, including the special dynamic forces T and L that are characteristic of the specialized function of the gantry or crane girders, that is to support the rails on which the overhead traveling cranes move. The structural analysis of gantry girders or crane girders can be considerably simplified using the following simplifying assumptions. Well, recall that theoretically the gantry girder or crane girder is subjected to biaxial bending combined with torsion. However, based on the idealizations presented in the previous slide, for visualizing or intuitively understanding the real physical behavior or structural response of the gantry or the crane girder, the structural behavior may be idealized for simplicity in design by assuming that the vertical force, that is denoted as capital V, and that acts due to the weight of the crane and its payload, as well as the self weight of the crane girder or the gantry girder, and the rail on which the overhead traveling crane is supported at either end, as well as the horizontal longitudinal dynamic design force L acting in the longitudinal y direction or along the outer plane axis for the figure in this slide, are resisted by the entire cross section of the crane girder or gantry girder, bending about its major axis XX, that is, bending of the cross section of the gantry girder or the crane girder in the YZ plane about the major axis of the cross section XX. While the horizontal transverse dynamic force T, that is induced by the acceleration and braking of the loaded trolley or crab of the overhead electric crane and the swinging of the suspended payload of the crane, that is denoted as capital T, is resisted only by the top flange of the gantry girder cross section, that is assumed to resist the entire horizontal dynamic transverse force T in bending about the minor axis ZZ, that is bending of the top flange in its own plane, that is the X Y plane. X Y plane. Thus, for simplicity in structural analysis and design of gantry girders, it is customary to assume that the vertical as well as the horizontal longitudinal dynamic design force L are resisted by the entire cross section of the steel crane gantry girder in bending about its major axis XX, that is, bending of the entire steel gantry girder cross section in the YZ plane about the major axis XX of the cross section. While the horizontal dynamic longitudinal the horizontal dynamic transverse force denoted as capital T acting in the transverse X direction as shown in this figure with reference to the coordinate axis defined in the schematic diagram of the industrial building structure presented in one of the earlier slides, is resisted only by the top flange of the steel gantry girder as depicted in this particular figure labeled Roman numeral 2, wherein the top flange is assumed to resist the entire horizontal dynamic transverse force T by bending in its own plane, that is the X Y plane about the minor axis ZZ of the gantry girder cross section. Thus, in effect, the simplifying assumption numbered Roman numeral 2 that is implemented for simplicity in the structural analysis and structural design of the steel gantry girder implies that the entire horizontal dynamic transverse force T is resisted completely by the top flange of the steel gantry girder bending about the minor axis ZZ of the gantry girder cross section as shown in this figure numbered Roman numeral 2, thus ignoring the stiffness or the contribution of the remaining part of the gantry girder cross section, that is, ignoring the stiffness and the contribution of the web as well as the bottom flange of the gantry girder cross section. A conservative assumption. Therefore, because while in reality the horizontal dynamic transverse force denoted as T is resisted by the entire cross section of the steel gantry girder that undergoes bending about the minor axis ZZ as well as torsion about the longitudinal axis Y, resulting in rather complex physical behavior in reality. The structural analysis of the steel girder, that is the steel gantry girder cross section, may be performed by implementing the second simplifying assumption, wherein we assume that the total horizontal transverse dynamic force T induced by the acceleration and braking of the loaded trolley or the crab of the crane, as well as the swinging of the payload of the crane, is resisted only by the top flange bending in its own plane, that is the XY plane about the minor axis ZZ of the girder cross section. Since the assumption results in a more conservative, that is, higher or safer estimate of the normal and shear stresses in the girder cross section. Therefore, utilizing or implementing these two simplifying assumptions for the structural analysis of steel gantry girders or steel crane girders subjected to combination of concentrated loads acting at the level of the top flange of the gantry girder cross section, that is combination of the vertical design force V due to the weight of the crane and its payload, including the self weight of the gantry girder itself and the self weight of the rail that is installed on the top flange of the gantry girder. The horizontal dynamic longitudinal force L acting in the longitudinal y direction of the industrial building, induced by the acceleration and braking, that is the surge and impact of the crane as a whole, and the horizontal transverse dynamic force denoted as capital T, that is generated by the acceleration and braking of the loaded trolley and crab in the transverse X direction of the industrial building, including the swinging of the suspended payload in the transverse X direction. The complex structural response that is involved in the real structural behavior or real physical behavior of the steel gantry girder under the combined action of all these three concentrated design forces or design loads acting at the level of the top flange may therefore be modeled or idealized for simplicity in structural analysis and design by implementing assumptions 1 and 2 presented in this slide. It is worthwhile to note here that while considering the uniaxial bending of the top flange about the minor axis ZZ of the beam cross section, it may be assumed that the top flange, that is deemed to resist the entire horizontal transverse dynamic force capital T by bending in its own plane, that is the XY plane, or bending about the minor axis ZZ of the girder cross section, is supported in the orthogonal direction, that is the direction perpendicular to the bending of the top flange. Due to the large stiffness or the large in-plane rigidity of the web of the gantry girdle. In other words, while considering the uniaxial bending of the top flange of the gantry girdle in its own plane, that is about the minor axis ZZ of the girdle cross section, to resist or accommodate the entire or total horizontal transverse dynamic force, capital T, thus ignoring the contribution of the remaining part of the cross section, that is the beam, that is the web and the bottom flange, as signified by the break symbol here, as well as the dashed lines representing the web and the bottom flange. It is assumed that the top flange is supported in the orthogonal direction, that is the direction perpendicular to the plane of the bending of the top flange, and is thus considered to be laterally supported against uniaxial bending in its own plane by the web of the girder due to the large stiffness of the web in the vertical direction. Thus, based on the above mentioned simplifying idealizations that are implemented for the simplification of the structural analysis and for consequent simplicity in design practice, and are also rational and realistic, as the simplifying assumptions do not result in any significant loss of accuracy in the calculation of the normal and shear stresses in the gantry girder cross section. The design equation for the limiting values of the ultimate moments that are the bending moments about the major axis XX and the ultimate value of the bending moment about the minor axis ZZ are governed by the following interaction relationship. Since the design problem based on the bending of the steel gantry girder about the major axis XX and bending of the top flange in isolation about the minor axis ZZ involves biaxial moments, that is, moments about bending moments about two different axes, that is the major axis XX and the minor axis ZZ of the crane girder cross section or the gantry girder cross section. The design formulation that governs the limiting values of the ultimate moments about the two different axes, that is the major axis XX and the minor axis ZZ of the gantry girder cross section, is an interaction relationship as the bending moments about the two different axes, that is the major axis XX and the minor axis ZZ of the gantry girder cross section, are biaxial or acting in acting along different axes, and the interaction equation governing the limiting values of the ultimate moments therefore may be presented in the format shown in this equation, or relationship, wherein the term in the first curved parenthesis represents the ratio of the ultimate moment, that is ultimate bending moment, due to the action of the vertical design force V and the horizontal dynamic transverse force L about the major axis XX of the girder cross section to the corresponding design moment denoted as capital M subscript D X, where the subscript capital D signifies the design moment, while the subscript X signifies that the design moment M subscript D is about the major axis XX, while the superscript girder signifies that the design moment capital M subscript capital D subscript X is the design moment for the entire girder cross section as depicted in figure on the left hand side, numbered Roman numeral 1. While the term in the second curved parenthesis presents the ratio of the ultimate bending moment denoted as capital M subscript small u subscript small z, where the subscript small u denotes ultimate moment while subscript small z denotes that the ultimate moment is being calculated about the minor axis ZZ of the girder cross section, whereas the superscript capital T signifies that the ultimate bending moment MUZ about the minor axis of the girder cross section is induced by the horizontal dynamic transverse force T, and the ratio of the ultimate bending moment MUZ about the minor axis ZZ of the girder cross section induced by the horizontal dynamic transverse force T to the design moment of the top flange only, as it is assumed that the entire horizontal dynamic transverse force and the resulting ultimate bending moment due to the horizontal dynamic transverse force T about the minor axis ZZ is resisted only by the top flange of the girder cross section and is denoted as the bending moment capital M subscript UZ superscript capital T, the ratio of which to the limiting value of the bending moment, that is the design value or the design moment, is denoted as capital M subscript capital D subscript D, where subscript capital D signifies that the denominator is the limiting value of the corresponding ultimate bending moment, that is the design value or the design bending moment about the minor axis ZZ of the girder, while the superscript top flange signifies that only the cross section of the top flange is considered for calculating the limiting value of the bending moment about the minor axis ZZ. That is, the design moment denoted as capital M subscript capital D subscript Z is based only on the cross section of the top flange or the stiffness of the top flange, as signified by the superscript top flange in the notation for the design bending moment capital M subscript capital D Z. For the design moment of the top flange bending in its own plane, that is the XY plane, or bending about the minor axis ZZ of the girdle cross section. And the interaction equation, therefore, as presented in this formulation, may be graphically represented by this interaction envelope or limiting envelope for alpha equal to 1, where alpha is the power to which these ratios have been provided. For alpha equal to 1, which is the simplest and the most conservative representation of the limiting envelope or the envelope of the limiting values of the ultimate bending moments about the major axis XX and the minor axis ZZ of the girdle cross section. For alpha equal to 1, the interaction equation is graphically represented by this linear limiting envelope. One may also visualize this linear limiting envelope as depicted by the straight line in this figure as the failure envelope for the value of alpha equal to 1, which results in the most straightforward and conservative estimate of the limiting values of the ultimate bending moments about the two axes, that is the major axis XX and the minor axis YY of the crane girdle cross section. One may note that if alpha is equal to 2, then this envelope as modeled by this general interaction equation will result in a circular envelope, rather. Or an envelope that follows the locus of a circle. However, for simplicity in computation as well as conservative design, alpha is generally assumed to be 1. That is, the power of these ratios is generally assumed to be 1. And for alpha equal to 1, the design equation is simplified to a linear equation, that is, equation for a linear envelope, linear limiting envelope as shown in this figure, which is also the most conservative limiting envelope, that is, limiting envelope that results in the safest values of the limiting ultimate bending moments about the major axis xx and the minor axis zz.